So wavefronts move with the waves and are perpendicular to the direction of the wave's motion. So if there's a wave, it's going that way, then the wavefronts look like this. And the rays go in the direction of the wave's energy transfer and are perpendicular to the wavefront. So a ray will be like this, like that. When a wave in a medium meets a boundary, it can be reflected or transmitted or both. So if some light goes like this, then some of it can get reflected off and some of it can go through. And the wave's speed is what determines what happens. And wave speed usually changes when it moves between mediums. So if this is what we're doing here, and light comes, then its speed is going to change, which causes it to refract. And remember that the frequency never changes, but the wavelength of the light changes, or any wave changes when it moves mediums, and the speed changes. So for full reflection, the angle of incidence is equal to the angle of refraction. So if all of the light, none of it goes through like this, this doesn't happen, then this angle here is equal to this angle here. And remember that the angle is to this normal, not like this or something. And for transmission into a different medium with refraction, the wavelength decreases because the density of the wave has to increase. Like in the water here, the wavelength decreases, but the density, so the density does increase because the speed also changes, and it will be slower, so the wavelength should decrease because of the formula in the formula. And Snell's law is that V1 over V2 equal to sine theta 1 over sine theta 2. And this is for a wave going between two mediums. And that theta is this angle here and this angle here, where V1 is the speed of the first and V2 is the speed of the second. The refractive index is c divided by the speed of light in the medium, and it's called m. And for air, the refractive index is pretty much 1 because v is pretty much 1. So the refractive index of glass with respect to water, you can do it pretty much the same as if the water was the light. So n of glass with respect to n of water is equal to, as you what's in the formula booklet, the V of water over the V of glass. And using the formula for the refractive index, n is equal to c over, so for glass, it would be V, and this is equal to 1.5 equals C over V glass. So the V of the glass is equal to C over 1.5, and you can do the same thing for the V of water is equal to C over 1.33. So the V of water is equal to C over 1.33, and you can just multiply by the opposite. Okay, 1.5 over C, and C cancel 1.5 over 1.33, and this is equal to 1.13 approximately. So that's the answer for A. So for the second part of the question, we can use the other formula, sine theta 1 over sine theta 2 is equal to n2 over n1 and I'm just rearranging what's in the formula booklet. So the angle of incidence when it's going in is sine 25, which is equal to tan 2, which is of the glass, because it's going into the glass, which is 1.5 over 1.33 is over sine theta 2, which is what we are looking for. And so if you just solve this for sine theta 2, you'll get that it is equal to 0.3747. So if you just take the inverse sine of both sides, theta 2 is equal to 22 degrees. They say that water has greater optical density than air because it's denser and light refracts in it. So something that is getting reflected away from the normal, like when it's going from dense to not dense, eventually will be in line with the thing that it's refracting. So if this is water here and it's going to the air, then it's going to refract away from the normal. And eventually, if the angle is small enough, then it will refract right here. And this is called the critical angle of the medium. And when the angle goes past the critical angle, this is the water, then the light will completely refract. And this is total internal reflection, because the speed change is too great to allow propagation of light into the air. So you can use the formula that's in the formula booklet and just put sine of 90 is equal to 1, and 90 is the theta 2. So sine theta 2 equals 1, and then you can just use the formula. So when two waves or more meet, the displacements of them add, which is called superposition. And constructive interference is when it gets bigger, and destructive interference is when it gets small or disappears. So get this wave, and this wave added right here, it'll probably get bigger, because say this is the middle, so like here, they're both positive, so it's gonna get bigger. Here, they're both negative, so it's gonna get bigger. But like, this one here is positive, this one here is negative, so that is destructive interference. And diffraction is when the waves go around corners. So I just say there's like a corner here, and there's like a wave coming, and it's gonna kind of go like that. And this is the most obvious when the size of the obstacle is the same size as the wavelength or smaller. So usually, so the amplitude of the wave gets smaller because, as you can see, it goes out through there's more of it, so the amplitude has to be smaller to conserve energy. And diffraction of light happens when light gets shined through slits, like in this diagram. And the frequency does not change, and neither does the speed or the wavelength of the wave. So this next part is only for HL, so if you're SL, just go to sleep for a bit. So when light passes through the slit, then you can see a diffraction pattern on the screen back here. So this diffraction pattern for one slit has an intense and bright central maximum. So let's draw it kind of like this. And then on the sides there's areas of minimum, and then there's little things like that. And these things are called minimums, and these are maximums. And shorter wavelengths diffract less. So if you shine, red would diffract more than blue. So the maxima here is much wider. But if the light was blue, then it would be much narrower, because it doesn't diffract as much. So the max and the mins are closer for blue light than in red light. And if you change the width of the slit, then the pattern spreads out more. So with a very narrow slit, like this, then the pattern will be spread out and less intense. So it will be more like this. But if you increase the width of the slit, like that, then the central maximum will be much greater, and the intensity will be greater, and it's less spread out. So it looks like this. So the path difference is the difference between the wavelengths of two waves. So when waves are pi out of phase with each other, and they have path difference pi over 2, and that is destructive. So it would be like this. So if this is the middle, then all these waves add up and cancel to 0, which causes minimums. So when the light that's here diffracts, and the light that's here, the part that diffracts will go to the same spot on the screen. If these wavelengths have path difference of half a wavelength, then this will be a minimum at some angle theta. And the angle of the first minimum, if you shoot light at a screen, so the first minimum here, so this angle here, this is theta 1. And the formula for this is the wavelength divided by the width of the slit B. So this is B. And if they give you the distance to the first minimum and the distance to the screen, like this, and you know this distance, which is usually called big D, and you know this distance, which is S, which you will learn later, then this is like a minimum and a maximum, and like that. Then if you just like draw a triangle here, then if you call this theta, then define theta, tan theta is equal to S over G. So you can use that to find theta. And remember that if the angle is very small, then tan theta is about equal to theta. So you can just use theta equal to S over D. And to make sure the angle is small, like for example, tan of 0.1 radians is equal to 0.1003. And there's more. And you can see 0.1 is very close to this. So the angle of the first minimum is the wavelength divided by the width of the slit. So here it's 640 times 10 to the minus 9 divided by the width of the slit. 0.08 times 10 to the minus 3. And this is equal to 0.008 radians. So the width of the central maximum in millimeters for this drawing, then it looks like this, something like this, and this is theta, then this is also theta, so 2 theta, and we know that this distance here is 1.2 meters. So if we just solve initially, for theta, then theta is equal to this distance here divided by 1.2. So we can find the distance by doing 0.008 times 1.2. And that's the distance for 1. So if you just multiply both sides by 2, then we will get the full width of the central maximum. And this is equal to 0.0192 meters. So if you want in millimeters, just divide by 1,000, and it is 19.2 millimeters. Or if you want it, 19 millimeters. So to remove all the effects, if you get asked a question like what will increase the angular separation of the minima, then you can just look at this formula. So to increase this angle between the minima, then you can increase the wavelength or decrease the slit width. And intensity doesn't do anything to the width, and neither does the distance. Right, that's all. Come back. So coherence is when two waves have constant phase relationships, so you can see them. Like if two waves meet each other and they look the same, then you'll be able to see them with their constructive interference. And you need this to see interference. So double slit interference is when light goes through two slits, like this, and the light gets shined through, and it goes through both the slits. And the light should be shown from the center, so the light has the same phase when it goes through both slits, so it can be coherent and you can see it. And what you get on the screen here is alternating bright and dark fringes, kind of like that. They have equal spacing. And remember to use the formula in the formula booklet. The distance from the screen, D, has to be a lot bigger than this thing here, the distance between the slits, little d. So this is not a good drawing. And remember that the distance between this is S, the distance between the fringes. And this is the wavelength. So everyone knows how to use that one formula at the bottom with the S equals wavelength d over d. But most people know how to use the constructive and deconstructive intermediate stuff. So for this one, if d is at a minimum, then the wavelengths are 1/2 out of phase with each other because it's making a minimum. And because this is the first minimum, n is equal to 0. So using that deconstructive interference path difference formula, n plus 1/2 times the wavelength is equal to the path difference, which here is 0.06, and n is 0, so wavelength equals 0.12 or 12 centimeters. That's it for SL, so now the rest is all HL. So the model from before didn't take diffraction and interference effects into account at the same time, and modulation happens when you consider the diffraction of both slits. When considering diffraction like before, it looks like A. So A is if there's only interference happening. And in B, this is what a single slit looks like. So we already did this. And C is what happens really, and it's a combination of both of them. And that is called modulation. So for A, the double slit pattern of bright fringes is modulated by a wider single slit diffraction pattern because both of the slits have a finite width. And before, the assumption was that both the slits are infinitely thin, but really you wouldn't be able to see anything if this happened. So the single slit pattern has a minimum at theta 0, which results in a minimum of overall intensity. So for B, it's obvious that this angle theta is equal to the wavelength over the width of the slit. But if you draw it out, then to this angle here, as you can see from the graph, it's supposed to be the fifth bright spot in this little one. So if you just draw the triangle here, we know that this distance is S, and this distance is this big D. So if you draw the triangle like this, and then like this, then you can use the small angle thing, that sine theta is approximately equal to this theta, which is equal to the fifth fringe, because it's the fifth one, times S over T. And this is the same thing using the cell formula times the wavelength over little d. So if you can just equate these now, this would be equal to 5 times the wavelength over d, and the wavelengths cancel. So 5b is equal to d, and d is equal to 5 times 0.2 millimeters, which is equal to 1 millimeter. So for A, we can just use the normal formula that theta is equal to the wavelength over the distance, or the width of the slit, and B is equal to the wavelength over this. And this formula is for a single slit. So if we look at the single slit pattern, the minimum is at 2 times 10 to the minus 3 radian. So it's equal to 520 times 10 to the minus 9 the wavelength. And this is 2 times 10 to the minus 3. And for this, you will get 2.6 times 10 to the minus 4 meters for the width of the slit. So for part B, we have to do like before. So the distance between the slits. So you need to use the double slit part for this one. So if you count the maximums, then this is the first one, second one, third, fourth, 2, 3, 4, 5. But this one is actually the first one. So 2, 3, 4, 5. And it's supposed to be on the fifth one. So remember that sine theta is equal to 5 times the distance between the slits, because of that triangle thing from before. And rearrange the formula to know that this is the same as 5 times the wavelength over little d. So you can use sine theta is about equal to theta, which we know is 2 times 10 to the minus 3 is equal to 5 wavelength over d. And if you solve this for d, you should get 0.0013 meters. You also need to know about interference when there's lots of slits, and the amount of slits is called n. And when n increases, bright fringes stay in the same place but become narrower, and the intensity of these fringes is proportional to n squared. So if you look at this drawing here, this is the effect of increasing the amount of slits. And don't be tricked by this scale, because these 5 ones should be 25 times higher than the single slit one. This one should be 9 times, this one should be 4 times, etc. And this assumes that all the slits have constant slit separation. So even if there's 5 slits, then the 5 slits just occupy a bigger space than when there's not as many slits. because if they have the same separation and there's more of them, then they will be longer. And when there are lots of slits, it's called diffraction grading, like shining light through a grating. And make sure that these slits should be illuminated uniformly, like through a flashlight or something, or a laser, because it's pretty small, so this is not that hard. And to get the number of lines per millimeter, just do 1 over the distance between lines. And make sure you convert to meters and stuff too. And the other way around is also 1 over the lines per millimeter to get the distance between the lines. So if you look at this drawing here, there's first and second order maximum and zero order. And in the formula booklet, where n times the wavelength is equal to d sine theta, n is the order. So this one here is when n equals 1, and here is when n equals 2, and the middle n equals 0. And then obviously theta will be 0, so 0 equals 0, and that is good. And d is the distance between the slits in the grate. So this is the same as it was with the double slit, but now there's lots of slits and it's just the distance between two of them. And theta is the angle between the center and the nth maximum that you are looking at. So if n equals 2 here, if you put n equals 2 in the formula, then theta will give you the angle to n equals 2. But if you put n equals 1 into the formula, then it will give you this theta, where n equals 1. And remember that theta is not a minimum like in the other formula. And it is the angle to the maximum with the n. And to find the maximum amount or total amount of maxima, remember that sine theta is always less than or equal to 1. So n is less than d over the wavelength from this formula option. And wavelength equals d sine theta. So at most it can be equal to 1. So n wavelength equals d, and you get this thing here. So when n is equal to d over this, that is the maximum n. So n is always less than or equal to this. And you always have to round down because you can have 0.5 over maximum. So to calculate the line per millimeter, just use the formula as always. Wavelength equals d sine theta, and the angle between the central maximum to a first order, so n equals 1. So 573 times 10 to the minus 9 is equal to d, and sine of 9.9 degrees. So d is equal to 3.33 times 10 to the minus 6, and 1 over d, which is the number of lines which will be per meter, is 300,000. It's actually something like that, but this is per meter. So per millimeter, just divide by 1,000, and there are about 300 lines per millimeter. So for part B, you need to calculate how many maximas are present. So use the formula as always. So sine theta is always less than 1. So n over d is less than 1. And so we know lambda and d. So this means that n is less than t over the wavelength, which is the same as 30.33, etc. times 10 to the minus 6 divided by 573 times 10 to the minus 9, which is equal, so n is less than 5.816, which means that n has to be 5, because n is a real or an integer. But that's not it. So if n equals 5 is the maximum that you can see, then that means there's 5 on one side of the maximum, and then there's a maximum, and then there's 5 also on the other side. So the number of max present is 11 maximals. So if the light is replaced by this wavelength, then the angular separation between the two second order maxima, so we just write down the formula like always. So now n equals 2, and the wavelength is 640 times 10 to the minus 9, and this is equal to d is the same, and d is still 3.3327 times 10 to the minus 6, 10 to the minus 6 times sine theta. So you will get that sine theta is equal to 0.384 minus 1. So just do the inverse, and theta is equal to 22.5857. But the angle between the two second order maximums, so this is just the angle between from the center to 1, is 2 times this, so 2 theta to 45.17, or angle is 45.2 degrees.